Let's get started. My name is Anders Hejlsberg, and I'm a distinguished engineer at the developer division at Microsoft. I'm also the chief designer on the new C# programming language, which I'm here to give you an introduction of. Before we sort of get into the technical details of the language, I thought I'd give you an overview of some of the key design ideas that we had behind the language when we designed it. C# is what we call the first component-oriented language in the C and C++ family. It's also a language in which everything truly is an object. As another design goal, we had, the fact that we wanted this language to enable you to write the next generation of robust and durable software. And finally, we want to make sure in our language design that we preserve the investment that you probably already have in C and C++. I'm going to talk a little bit about these big ideas. As I said, we call C# the first component-oriented language in the C and C++ family. And what I mean by that is that in C#, the concepts that characterize components when you do component-oriented programming are all first class in the language. Concepts such as properties, methods, and events, design time and runtime attributes, and integrated documentation are all first-class concepts. They're not naming patterns or interfaces you have to implement or adapters you have to write in order to handle events. Rather, they're right there in the programming language. And what that means is it enables what I call one-stop programming. Basically, when you write components in C#, everything is in one place. There are no header files in the language. There are no IDL files or def files you have to write in order to describe a mapping to COM or how properties and events, exist in the component. And because everything is in one place, it means that C# code very easily can be embedded in other hosting environments. And a good example of that is how C# embeds in ASP Plus pages, and I'm sure some of you have probably already seen demos of that at the conference here. Another key idea is that we wanted everything in this language to be an object. And when I say be an object, I mean really be an object. And there are sort of two traditional views of this in programming languages today. If you take sort of the C++ or Java camp, these languages divide types into two categories. There are primitive types such as ints and floats and double, and they're magic. They have special blessed capabilities. And then there are classes which users can write, where you get extensibility, but there are certain things that you can't do with classes that you can do with the primitive types and vice versa. Now, it's not something new that we've caught on to here. Clearly, the programming language design discipline years ago realized that some unification is needed here. And so if you take languages like Smalltalk and Lisp, indeed, they do have the view that everything is an object, including ints and floats and the primitive types. But it comes at great performance cost. If you write code in Smalltalk and you're doing operations on doubles, for example, when you add two doubles, the result becomes a new object that is allocated on the heap, and you have to basically deal with, the overhead that happens because of memory allocation and so forth. In C# we have unified these concepts, but with no performance cost. I'm going to get into technically how that's possible, but let me just say up front that what that brings about is a very deep simplicity throughout the system. And perhaps even more importantly, it gives you really improved extensibility and reusability. Because the type system is unified in C#, you can actually write new primitive types. There's nothing magical about int and float in this language. And indeed, in the base class libraries in the .NET framework, we do provide you with new things that you can think of as primitive types, like a decimal type that gives you 28 digits of precision and no round-off errors, a whole family of SQL types that basically are representations of types as you know them in databases where, you can have an int column in a database, but that column can also be null. And we have types that express that and allow you to directly operate on database values. And of course, because the type system is unified, because everything can be treated as an object, things like collections and general data storage types work for all types, not just for classes and objects. A third design goal of ours was to enable you to write robust and durable software in this language. It means that the language was designed from the ground up with concepts such as garbage collections, exceptions, and type safety as first-class assumptions. Just to recap briefly, the benefit of garbage collection is that you have no memory leaks, no stray pointers. Exceptions give you robust error handling. It's not an afterthought, it's not age results of bools that you're returning. And type safety, of course, guarantees that you don't run into a whole other class of errors that result from uninitialized variables and unsafe casts. Now, a lot of these benefits, of course, are, in a sense, provided to C# by the common language runtime in the .NET framework. But it's important to note that this language was designed with these concepts in mind from the beginning. They're not sprinkled on afterwards. Another thing that we spent a lot of time thinking about in the language design is this boring thing called versioning. It's, how when I write version 1.0 of my component, am I ensured that when I write 2.0, 3.0, and 4.0, that my end user's code will continue to run? And indeed, if I'm going through an evolution of versions, but I also have dependencies on base class libraries that evolve along a different path, how do we ensure that we don't break your code and that you write software that truly is durable in time? And it's quite remarkable when you do language design how pervasive that problem actually becomes and how much thinking you have to apply to the problem to come up with correct solutions. I have some more slides on that, and I'll show you what I mean by that. Finally, we wanted to, in our language design, preserve your investment in programming, preserve your knowledge of C++. This language has a very close heritage from C++. Things such as namespaces exist, pointers are there, albeit only in unsafe code, and I'll explain what I mean by that later. We have unsafe types, we have enums, we have things that you've come to know and love in C++. In a sense, we have not made any unnecessary sacrifices. We've also focused very heavily on interoperability. Again, in our language design as well as in the design of the common language runtime, we truly believe that this is not an ivory tower approach to software development. It's not like, go out and throw away all the software you've already written. It's super important to give you great capabilities of interoperating with stuff that you've already written. And I think that is really increasingly what software design these days is about. And C# talks to anything out there that's worth talking to, XML, SOAP, COM, DLLs, any other .NET framework language. Finally, we already internally have, and our partners have millions of lines of C# code in the .NET platform. And consistently what we see reported back from users of the language is that if you know C++, this language has a very short learning curve. And also consistently, we hear people reporting dramatically increased productivity. So those are sort of the big four ideas. Now, whenever you were first acquainted with a new language, of course, we have to look at how does Hello World look. And here's Hello World in C#. It's short and to the point. We import the system namespace with a using directive, and then we write a class called hello. It has a main, and in there we use console.writeLine to write Hello World. And let me try and switch over to the, let's see, that was not how it's done. Do this, and do this. And let me just try and just show you Hello World. Here it is, precisely like it was on the slide. And, compiling it is a simple matter of firing up the C# compiler, giving it the source file name, and that has now produced hello.exe. And to run it, well, we just run it, and there it is.
You're having a problem here.
I am? Oh, sorry. Okay, did you see anything at all? Anyway, it's, I mean, how interesting is Hello World anyway? It's, okay, we'll shift off that monitor here. Let me see if I can go back. Okay. So with that out of the way, let me talk a little bit about what a C# program looks like. What is the structure of a C# program? And there are certain concepts in there that are important to understand. First of all C# code is organized in namespaces. And these namespaces can contain types and other namespaces. In other words, it's a hierarchical structure. You can have a namespace called foo with a class called bar. You can have a namespace foo with a, another namespace within it, with another namespace within it, with a class in it. So there's underlying the whole thing, a hierarchical way to organize your code. Type declarations, as I said, are contained in namespaces, and the kinds of types we have are classes, structs, interfaces, enums, and delegates. The new one here, perhaps, is delegates, and I will get into precisely what delegate is. And then within types, you can have members, constants, fields, methods, properties, and indexers. There are some new ones there. Events is a first-class thing. Operators, constructors, destructors. The thing that's interesting here, as I said, about the organization is that when you write code in C#, there are no header files. Everything is written in line. So when you write a declaration of a class and you put a method in the class, you also write the implementation of the method right there. There's no separate declaration and implementation. What that also means is there is no declaration order dependence in this language. It's not like you first have to include some stuff or forward declare some stuff before you can reference it. Any declaration can come anywhere, and the compiler will sort it out. Indeed, conceptually, when you compile a C# program, what you do is you give the compiler a list of all of the file names, and you say, you go figure it out. Just conceptually concatenate them all, compile it, sort it all out, and do the right thing. So it gives you a lot of flexibility as to how you organize your source code. You can arbitrarily merge and split source files, store them in whatever directory you want. As long as, when you compile, you just tell the compiler what all the files are. As a side note there, actually, I say conceptually we compile the whole thing. We actually do have incremental compilation. So once you've successfully compiled an image, we can incrementally update it also. Maybe I can ask the sound guy to get rid of this, this thing here. So I'm hearing about Fred. Here's a slide that shows you an example of the program structure. You see we start again by using some namespaces, in this case just the system namespace. And then we declare a namespace system.collections, and then in that we put a class called stack. And within stack, we declare, an instance variable called top, and then we have a push and a pop method. And you'll see in the pop method, if the stack is empty, we raise an exception. So that's how we handle errors. Namespaces, like in C++, are open-ended. So multiple source files can contribute to the same namespace. I could have another source file in my compilation that also says namespace system.collections, and all the types then go into that same namespace. So one of the key things when you look at a programming language is how does the type system of the programming language work? How is it put together? In C#, we categorize types. They sort of fall into two buckets, value types and reference types. And it sort of is a reflection of what are the semantics of the types. Value types, when you have a variable of a value type, it directly contains its data, and therefore it cannot be null. A good example of a value type is an int. When you declare an int, you set aside 32 bits in line on the stack or in your object. And when you assign to it, you simply move those 32 bits in and out of the variable. In the other category, reference types are, in a sense, type-safe pointers. I mean, you're familiar with pointers in C++. Reference types are always allocated. Well, a variable of a reference type contains a reference to an object that is always allocated in the heap. Therefore, reference types can be null, or variables of reference types can be null. There are two simple examples here of a value type and a reference type. You see a declaration of an int, which we set equal to 123, and sort of graphically what we end up with is a box that contains the bits representing 123. String, on the other hand, is a reference type, so when I declare a string, what I'm actually declaring is a reference to an object that contains the string. Just drilling into the next level of this classification, in the value types category, we have things like the primitive types, ints and floats and doubles, enums, and structs. And in the reference type category, we have classes, interfaces, arrays, and delegates. Those of you who know C++ will notice a difference here. In C++, struct and class are really pretty much the same thing. When you say struct, it just means all of my members are public, but other than that, there's really no difference. And if you want a reference to a class, you have to say, foo star. In C#, there are no stars. Rather, the semantics are given by the kind of type you're declaring. If you declare a struct, it is by value. So a struct essentially sets aside bits in line or right on the stack. If you declare a class, it is implied that you always have a reference to the class. The compiler comes with a set of predefined types. I'm just going to go over them here briefly. In the reference type category, we have the keyword object, which is sort of the root of everything, and we have string, which represents a string. We support signed and unsigned integral types in 8, 16, 32, and 64-bit sizes. All characters are Unicode, so they're 16 bits. In the floating point category, we have the two IEEE types, float and double. And then the decimal type I talked about earlier, which is a 128-bit thing. It's a scaled integer with 28 significant digits. And then finally, the logical type bool. Now, the thing that's interesting here about these built-in types is that all of these keywords, all of these names, are just aliases for types that are provided by the common language runtime. So int is simply an alias for system.int32. And you can look at the definition of system.int32 in the common language runtime or in the base classes. It has methods on it, et cetera, et cetera. It is indeed an object, but it is a value type, as I said. So there's this very deep integration and nothing magical about these built-in types. There's a question here: can they be extended? Yes, they can, and I'll take questions afterwards. But it's a good question. In fact, some of the slides here I think will show you how this works. Just going over, the kinds of types we have. I talked about classes. Classes in the common language runtime and in C# are single inheritance, but they do permit multiple interface implementations. And the kinds of members you can have in classes are listed here: constant fields, et cetera, et cetera, et cetera. New ones, if you're coming from C++, would be properties, indexers, and events. As you can see, these are first-class concepts. Members can be static members or instance members, pretty much the same as in C++. A static member, there's one copy in the universe. An instance member, there's one copy per object. And finally, types can be nested, so you can have classes within classes. We give you quite rich control over access to members. We have the same visibility specifiers as C++, so public, protected, and private. There's a fourth one called internal, which means it is internal to this compilation, to this project, meaning that every source file in this compilation can see the member, but outside of that, no one can see it. So I talked already about how there are some key differences between classes and structs, but the easiest way to think about structs is really to say they're like classes, except they're stored inline, they're not allocated on the heap. When you assign one struct to another, we copy the data, not the reference. And there's no inheritance with structs, or rather, all structs implicitly inherit from type object. Structs are ideal for lightweight objects like complex numbers, points and rectangles, color. And indeed, as I said, all the primitive types in the system are actually structs. Int and float and double are structs. Structs basically bridge the gap between primitive types and classes, is how to think of it. Now, benefits of structs are, because they're not heap allocated, they create much less GC pressure. Well, in fact, they create no GC pressure because there is no heap allocation going on. And of course, that gives you more efficient use of memory. Now, that said, we don't intend for people to run out and make everything a struct, because structs are essentially meaningful for things that are up to about 16 bytes in size, I would say, and things that have value semantics like numbers, like points and rectangles. Just to really hammer the point home here, here's a little graphic that shows a declaration of a point, that contains int x and int y, and I have two declarations here. One is a class, one is a struct. Indeed, within the curly braces, everything looks the same for the two. There are two instance variables, x and y, and presumably a constructor and so forth. Below that, you'll see me create instances of, well, first create variables of both types, and then create an instance of both types. So the CP variable is a class variable, and I assign to it a new instance of the class point. And likewise, the SP variable is a struct, and I assign a new instance of a struct. Now, one key thing to observe here is that the new operator means create me a new instance of this type. If the type is a reference type, that means allocated on the heap. If the type is a value type, it means allocated on the stack. So graphically here you see an example of what that really means. For the SP, for the struct variable, all I'm setting aside here is 64 bits, 2 ints. If I declare as a local variable, they're just allocated right there in a stack frame. For the class variable, when I declare a variable, what I'm really declaring is a reference. And what new returns is a reference of that type that's allocated to an instance that's allocated in the heap, has a V table that says I'm a point, et cetera, et cetera. And you can see there's more memory used to represent the class version than the struct version. So unlike C++, interfaces are a first-class construct in C#. Interfaces support multiple inheritance, but no implementation inheritance. You can't implement the methods in an interface other than by having a class implement the interface. Interfaces can contain methods, properties, indexers, and events. And we support a feature called private interface implementations, and it's really best described by an example here. Say I have an interface called databound, or iDatabound, and it has a bind method. And this is some internal worker interface that I need to implement in order to be data bindable. And let's say then that I'm declaring an edit control that inherits from a base class control and implements iDatabound. Now, I have two choices of implementing the interface here. I can just write a normal bind, a public bind method in my edit box, and that will implement the bind method of the interface. But when I do that, that public method also ends up as a public method on my edit box. And really, I don't want that to happen because this is like an internal interface that is really just an internal implementation detail. So we give you the option of writing private interface implementations, and that's what you see on the slide here, that the edit box contains directly an implementation of idatabound.bind. That method does not show up when you're using the edit box. Only by casting it to idatabound will you actually see that method. So it doesn't pollute the public profile of the class, so to speak. There are also other key reasons why we have this feature. Let's say you have two interfaces, idatabound and some other interface, and they both contain a bind method with the same signature. Unless we give you a way of qualifying the implementation, it would be impossible to have two different implementations of that method. So as I said, C# supports enums. Unlike C++, they're strongly typed, meaning that in C++, when you declare an enum, really what you're just declaring are some names for integral values. And you can freely use, values from every other enum type without getting type errors. That's not the case in C#. Enums are strongly typed. So if I have a foo enum and a bar enum and a method that takes a foo, I can't pass it bar.something, for example. So that eliminates a whole class of errors that often occurs with enums. We do support operators on enums. And furthermore, you can specify the underlying type of an enum. That's another omission in C++. Enums are always int-sized, which is a waste of space sometimes. And so we give you the option to specify sort of the underlying storage size of the enum. So I mentioned earlier that we have this thing called delegates. And really the way to think of delegates is they're object-oriented function pointers. Now, a function pointer, I'm sure you're all familiar with, it's a thing that points to the entry point of a function, and through the function pointer you can invoke the function. And part of the type of the function pointer is the signature of the function. That is, what parameters does it take and what type does it return. However, a function pointer only points to the entry point of some function. A delegate, unlike a function pointer, can also point to a method of an object. So a delegate, in a sense, is a combination of a reference to an object and a method on that object. And when you invoke through a delegate, you are invoking that method on that object. Delegates are the foundation for events in the entire .NET framework. And basically, in order to support multicasting of events where, multiple receivers, multiple handlers have registered an interest in handling an event, delegates support plus and minus operations. You can actually take two delegates or two function pointers and add them. And what you get is a new function pointer that when you invoke through it, it invokes first the one function pointer and then the other. Here are some examples of declarations of delegates. There is a mouse event declared here, that takes an int x and an int y and returns void. Another one is like a mathematical function that takes a double and returns a double. And in order to create a delegate onto a particular function, we simply new the delegate and pass it, the object and the method. So here we're creating a delegate onto the sign method in the math class or the math object. An invocation is just like a function pointer. So I'm going to go back now to this unification of the type system that I talked about earlier. In C#, everything is an object. And what I mean by that is that all types ultimately inherit from object. Now, before we get into how that actually is possible, what the ramification of this is that any piece of data can be stored, transported, and manipulated with no extra work. You simply put it in an object or treat it as an object, and you can carry it around. It is always self-describing. It always tells you what type it is. If you look at the inheritance hierarchy, here all the blue boxes are just classes. So we have object, and then we have a stream class, and from that we have memory stream and file stream, and we may have a hash table. But also int and double inherit from object. Now, the thing that makes that possible without a loss of performance is a mechanism that we call boxing and unboxing. If you think about what I said, that everything inherits from object, and just live that out, well, that means that it must be possible to write the code that I wrote here, where I first declare an int, give it a value, and then I assign it to an object. Well, because it inherits from object, it is assignment compatible with object. And later, it is also possible to take that object and cast it back to int. Now, what does that physically actually do? The mechanism that makes this possible is boxing and unboxing. If you look at the little graphic below the statements, the first statement declares an int and puts a value 123 into it, and so now we have 32 bits containing the value 123. When I assign that int to an object, whenever I assign a value type to an object, the system boxes the value. So it allocates on the heap an object, puts the value into it, and tags the object with the type of the variable. So here, what I end up with is a little object on the heap that contains the value 123 and dynamically says I am an int. So it in a sense has a v-table that says I'm an int. So later, I can walk back up to that object and say, coerce me back to int, just like I can downcast a class. And what the system does there is it checks, well, geez, does the object, first of all, is it non-null? Does it reference a box that contains an int? And if so, the operation succeeds. We fish the value back out. Otherwise, an exception is raised. So what does this mean? Well, first of all, it means that you never have to write any wrapper classes. If you want to transport a piece of data around, and that piece of data so happens to be a primitive type, you can simply treat it as an object. You don't first have to create a class that contains a field of that type and then instantiate that and then carry that around as an object. And of course, it also means that our collection classes work with all types. But perhaps most important, it means the death of variant. Thank you. Everything in the .NET framework is an object. Now, some examples of use of this, and believe me, there are plenty in the framework, is, say, the formatting function that the string class declares. It's sort of like printf, but it's type safe. So it gives you the ability to specify a formatting string with some placeholders for the arguments, and then it takes a variable number of objects. And because everything is an object, we could actually pass it, in this case here, a total that might be a float and a date that might be a date time. And the system will simply box those, pass them on to the formatting function. And indeed, the formatting function internally can turn around and ask these objects, what type are you? And the object says, oh, I'm an int. And even further, these things can implement interfaces. So the formatting function can actually turn around and ask the int to please format itself to a string. So you see, there's really like this true deep simplification that this brings about. Now, of course, it also means that, as I said, our collection classes work with all types. So if I want to have a hash table that maps from integral values to their string representation, well, of course I can do that. The hash table has an add method that takes two objects, one the key, one the value, but I can use ints as the key if I so prefer, and that's what I'm doing here. So I'm going to turn now to some of the stuff I was talking about as one of our design goals, component development. And as I said earlier, a component is defined by things like properties, methods, events, integrated help and documentation, and design time information, that the component, and runtime information that the component carries around. C# has first-class support for all of these notions. It's not naming patterns, it's not adapters, it's not, complicated interfaces that you have to implement, and it is not done through external files like idle files that you have to write and then sort of mentally correlate, your class and all of this additional information that sits out here. And really, the net result is that components are incredibly easy to build and consume in this language. So drilling in a little bit into properties. Properties are sort of like smart fields. That's at least how I think of them. You're all familiar with the ability to declare fields or instance variables in a class. And really, if you think about it, what characterizes a field? Well, it has a type, and then it has two things it can do. You can either load values out of it or store values into it. Properties are like that, but they give you more control. They're still named entities, and they still have the notion of getting and setting the value, of reading and writing the value, but you get to write code that controls what happens when you do that. If you look at here, I have a little example of a button which inherits from a base class called control, and then it declares, an internal private variable called caption, lowercase caption here. And then we have a property called caption, uppercase caption, and it looks just like a field declaration, except I follow it with an open curly, and then I specify the code to execute to get the value of the property and to set the value of the property. So in my case here, to get the value of the property, I just return the value that I'm storing in my internal variable. But when I set the value of the property, well, I store the new value, and then I repaint the control. So when the user assigns a new caption to the button, it updates itself on the screen. Indeed, the purple box here shows you, well, what does this look like in use? Well, you can create a new button, and then you can assign a caption to the button, and you can later fish the caption out. Now, you can actually have read-only and write-only properties by omitting either the getter or the setter. But as you see, it's a very natural syntax. It allows users to truly think of objects having properties. Now, some of you might think, well, geez, isn't this inefficient? You're executing this code every time you get the value of a property or every time you set the value of a property. Well, actually, no, it's not. C# generates MSIL, our intermediate language, which then either at install time or at runtime is translated into native code by a JIT compiler. And the JIT compiler is smart. It will inline properties if they just refer to instance variables. So this is no less efficient than using an instance variable, but it gives you great flexibility in that later down the line, you can change the property from being an instance variable to being some other storage mechanism, maybe it forwards to someone else, without breaking existing code. So it gives you a lot more flexibility. Just like properties are the ability to have smart fields, so are indexers the ability to have smart arrays. When I declare a property, I'm really, in a sense, declaring what does it mean to, given an object instance, to say object instance dot foo, if the property is called foo. Well, in the same way, indexers give you the ability to control what it means to say object instance bracket something, to index it. And one example might be staying, with the control metaphor here, a list box that contains a list of items. If you look at the implementation here, well, internally it'll declare a string array that stores the items in the list box, and then it declares an indexer, which sort of looks like a property but has the name this and has an argument list in brackets. And what it really is saying here is what it means to index this with an int. It is an operation that returns a string. And then again, I write accessors, a getter and a setter, that either stuffs the value into my internal storage or takes the value out. And indeed, when I set it again, I go repaint my list. So users can index it like an array, but things are appropriately updated. And here over in the purple box, you again see example of what it looks like in use. One of the things that's interesting about indexers is that they can be overloaded just like methods and constructors can. So I can actually say I'm implementing something like a dictionary or a hash table that can be indexed by int, but also indexed by string, the key. Indeed, I can just declare what does it mean to index this by string, what does it mean to index this by int, and write the code for that. So this gives you a very flexible way of building, what appears to be smart arrays. So events are first class in C#. They're a language construct. And when talking about events, there are sort of two sides to the issue. There's like, how do you become a source of an event? How do you become someone who can fire an event? And then there's how do you consume an event that some other object sets off? And looking first at how you source events, the first thing you typically do is you declare a delegate with the signature of the event. In other words, you declare a type that specifies what is the argument list and the return type of the event. In this case here, I'm declaring an event handler that takes an object and an event args instance and returns void. Now, to then actually define the event and the firing logic of the event, I have my little button class again here, and in order to declare a click event in my button class, I need to write one line of code, public event handler click. This button now has a click event that's available to the outside world. In order to fire the event, in my little onClick method here, this is sort of part of the internal logic of my button. When firing the event, I simply check, is the click delegate not equal to null? And meaning, is someone listening? And if so, then I invoke. And as I told you earlier, delegates support the notion of multicasting, so there could actually be multiple listeners listening to this event. To handle events, you basically define and register an event handler. I hate this word register because this has nothing to do with the registry, of course. But giving you an example here, let's say I'm creating a form that has a button on it. The button can fire click events, and I want to write handlers for that click event. I want to have an OK button on my form. So I declare my form that inherits from the base class form in the .NET framework. I declare a button called OK button, and then in the constructor of my form, I instantiate the button. I set its caption to be OK, and then I attach an event handler for the click event. Now, if you look first to the right here, I'm instantiating an event handler onto the OK button click method in my class. And then in order to register it, I simply use the plus equals operator. I attach it onto the click event. Indeed, I could do multiple plus equals and attach multiple handlers, and I could do minus equal to get rid of them. It's completely dynamic. And of course, when the event happens, then all I see is that the OK button click is invoked. Now, I want to assure you also that this stuff is incredibly fast. Invoking through a delegate is literally like making an indirect function call instruction. So this stuff is very fast, but it's type safe as well, and it gives you multicasting and so forth. Another key feature in C# is a thing called attributes, and this is a whole new thing. It hasn't really, I haven't seen it in any other programming language, so I'm going to try and explain it to you. Attributes are basically about answering the question on the slide here. How do I associate information with types and members? Like, how do I specify what is the documentation URL for a class? How do I specify what is the transaction context for a method? How does a class persist to XML? Or dream up your own favorite question. We already support in C# the notion of putting declarative information on types and members, like saying this thing is public, this thing is private. Attributes are an extensible way of putting additional information in that same spot. You know, like saying, yes, this thing is public, and oh, its documentation URL is this, and its XML mapping is that, and so forth. Traditional solutions to this problems are the language designers add new keywords or pragmas to the language and determines, you know, the close-ended set of possible things that can go on a declaration. Another solution might be to use external files like idle files and def files. Key here is that neither of those solutions are extensible. C# takes a different view of it and supports the concept called attributes. And I think the best way to understand attributes is first to look at an example of attributes in use. And this is actually kind of a real-world example. This is something you might build with the .NET framework. Let's say you're building a web service, and you have an order processor class, and that class has a submit order method that can be invoked, you know, over the web as a web service. Well, first of all, we somehow want to indicate to the system that this method could be a web service as opposed to this other public method which doesn't want to be a web service. And so there's this attribute here, web method, that we put on. Likewise, this thing takes a purchase order argument. Well, that thing, of course, if it's a web service, has to be transported in XML, and we want to say something about how it gets transported in XML. We want to say something about the schema of that XML. So we want to say that, you know, when a purchase order becomes XML, the root tag should be an order tag, and for each of the fields in the object, like the ship to field, we want that to be a ship to element in the XML, et cetera, but the order date, we want that to be a date attribute that goes inside the tag in XML. So you see here an example of adding all of this declarative information, but adding it right in place, right there with your source code. And the thing that makes that possible is attributes. Now, you may ask, well, what are attributes? Where did these things come from, this web method thing, and this XML root and XML element and so forth? Well, attributes are actually classes that you could have built or that the framework could have provided. They're simply classes that inherit from system.attribute. These classes, of course, will have constructors and they will have properties and so forth. And those constructors actually define how I can write them as attributes. So the XML element attribute has a constructor that takes a string argument. Because it inherits from system.attribute, I'm permitted to use it as an attribute. Because it has a constructor that takes a string argument, the compiler knows that when you use that attribute, you must give it a string argument. Now, what happens in reality is that when we compile this, these attributes sort of get pickled away in the metadata for the class, and then they can later be reflected upon by the reflection system. So later, at runtime, the system can walk up to an instance of purchase order and ask it, do you have an XML root attribute? And the thing can say no, or it can say, yes, I do. Well, then please give me an instance. And at that point, we have the information available to, in a sense, create the instance using these constructor arguments, and in a type-safe fashion, give it back to you. So you can see how this is a truly extensible mechanism for hanging additional declarative information onto types and members, and then examining them dynamically at runtime. We have extensive use of attributes in the .NET framework. You saw an example here of how we use it to express XML mapping and web services. We also use it in security, in serialization, in our component model, in interoperability with COM and DLLs, code configuration, et cetera, et cetera. But key is that it's an extensible mechanism. If you are developing hosting environments that require declarative information carried along by the components that you host, there is a mechanism here that allows you to build that. Finally, when talking about components, a really key thing about component development is that you want to be able to write documentation for the component in a disciplined way. And ideally, you really want to write the documentation alongside with the class. And to support that, we've introduced the notion of XML comments that you can write in your source code. The way it works is essentially that any line that starts with 3 slashes is considered an XML comment if you tell the compiler to be interested in XML comments. What the compiler then does is it gathers up all of these XML comments. It validates the XML, and then it puts elements around the XML that say where it came from, and then it dumps it all into an XML file that you can then post-process either with a style sheet or some XML transformation into HTML. The cool thing about it, though, is that it's completely extensible. It's yet another example of where we have really thought hard about the problem and approached it in an extensible fashion. Yes, we validate the XML you write, but we don't say anything about what the tag names you use in there are. So if in your corporation you have one particular standard for documenting stuff, or there's something else that comes along later that you want to present in your documentation, you can add new tags. We will check for you that they correctly balance out, but we don't actually say anything about what kinds of tags you can use. I'll try and show you a little demo of this. Let me see if I can. That one does not look too happy, does it? Maybe you can look. Oh, geez. And I think we lost our technician, too. Can you see anything on these screens at all? Oh, there we go. Oh, this is terrible. What's that? I don't know. Okay, now we're looking.
Go to like the number 4.
Okay, let me do that. Just try another cable here if I can find it.
It's the number 4 cable.
Here we go. Okay. Try number 4 instead.
Number 4.
Okay. Looking better? Hey, look at that. Real-time debugging. Let's see. So let me first show you here an example of a C# source file, pretty large one actually. This is some of the sources for the XML parser that's built into the framework. And you can see in here there's extensive documentation of these classes. Here's XML string, and there's a summary of what it does, remarks, et cetera, et cetera. All of the methods are documented with this XML in-source documentation. Now, I can compile this with the C# compiler, and I can say, please extract all the documentation and put it into t.xml. And this produces the executable and also t.xml sitting right here. And now I can fire up my browser on that, start t.xml. And here you see the extracted XML. So you saw I had an XML string type that had a comment on it, an XML declaration on it, or description on it, and you see how that has been put into an XML tree here by the browser. And you see how the compiler has added additional information around the extracted XML that says where it came from, so that a post-processing tool can figure out, what to do with this documentation. Now, the really cool thing is that one of our technologies is called style sheets, or XSLT. And I can actually, let me first try it and show you here a little style sheet for these for XML as we write it, with summary tags and so forth. Here's a style sheet that contains descriptions of what transformations need to occur on this XML in order to make HTML out of it. And what I can actually do is I can just copy this line here and then fire up t.xml and paste it in here. So I'm just going to add one line to that file that the compiler output that references a style sheet. And now when I reference this XML file in my browser, the style sheet will be applied, and I will look at it in a style sheet transformation instead. So if I save it here, go back to the browser, and refresh, you'll see all of a sudden that my documentation is now nicely presented. I can scroll through it and so forth. Okay, I'm going to jiggle this again. All right, we're back. So the bulk of the code you write, of course, ends up sitting in statements and expressions. And C# has a very high fidelity with C++ in the area of statements and expressions. I mean, you'll immediately feel at home in this language. However, we have, labored to remove some of the kinks, if you will, in C and C++. For example, in C and C++, if, while, and do take an int expression. And that means you can write silly code like if I equals 1, then blah, blah, blah. And what will happen is that I gets assigned the value 1, and the if branch always executes. And that's probably not what you meant. We require bool conditions, and that piece of code will be an error in C#. Likewise, we do not permit gotos to jump into blocks simply because it just doesn't make sense to do so. The switch statement does not permit fall through. Now, what that means is that when you write a switch statement, every case in the switch statement must end with a break, or must the code sort of at the bottom of the case must be unreachable. But if there's a possibility of fall through, then you get a compile time error. And you must then manually specify go to case or go to default to jump to another case. This eliminates a whole class of errors that actually are very real. Someone told me how the New York telephone exchange at one point shut down for a whole day, and they finally traced the bug back to a fall through in a case statement. So these problems are real. We have a for each statement that allows you to iterate collections and arrays. We have checked and unchecked statements that allow you to control overflow checking on int operations. And finally, we have a rule that say expression statements must do work or must have the possibility of side effects. And that is sort of the flip side of the first rule I talked about with the if, while, and do. And it says, you can't just write an expression and throw away the result. There must possibly be something happening here, like a function call. So, writing I equals 1 is an error, where in C++ it means compare I to 1 and throw away the result. So the for each statement allows you to iterate arrays, first of all. Say I have my main that takes a string array, of the arguments that I specified on the command line. I could simply say for each string s in args, write out the string. But more importantly, we also support iteration of user-defined collections. So if you create a collection, and in that collection you add an enumerator, you implement a method that can get an enumerator on the collection, then the for each statement will generate code that obtains an enumerator and then enumerates through the collection. So you can write nice code like, let's say I have a customers table here that has an order by method that can order by the name column and return me another collection. I can then iterate on that collection simply using a for each statement. So it leads to some simplification of your code. C# supports parameter arrays, and they're really, in a sense, the type-safe version of var args in C++. I'm sure you all know the printf method, and if you've never looked at how it's implemented using var args. And var args is very powerful and also very dangerous because it's not type-safe. In C#, again, we leverage, the notion of boxing and the unified type system, and then go one step further and allow you to have parameter arrays. And here's an example of how you would declare something like printf in C#. You basically declare it as a method that takes first a string, a formatting string, and then an array of objects. And by using the params keyword, which you can apply to the last argument of a function, you are specifying that, by the way, the user can give me this array by just writing a comma-separated list of objects. And since anything can be an object, they can basically write a comma-separated list of anything in an invocation. And indeed, you see an example of it down here, where we're passing a string and 2 ints. And what the compiler actually does for you is create an array, stuff the values in there, and pass the array on in a completely type-safe fashion. C# supports operator overloading, and I think the key to that is that it allows you to create first-class user-defined data types. It's used extensively in the base class library. We have predefined types in the base class library, like a decimal type I talked about. We also have date time and time span that support operations like, you can add a time span to a date time and get a date that is offset by that time. We use it in the frameworks for points and rectangles, and we use it in SQL integration, as I talked about earlier, for a whole family of SQL types provided by the base class libraries. Here's a brief example. I'm not going to dwell on it too much. In fact, after my talk, Joe will be repeating his advanced C# talk, and he will go into it in more detail. He'll be repeating it in the same room. But here's just a brief example of how would I declare one of these database ints. An int that can have all the possible values of an integer or be null as a database column. And basically, I first, declare it as a struct. It's a value type. It has value semantics. It doesn't require heap allocation. I have some instance data here, the value of the int, and a bool that says whether or not the int is null. And then I can have an isNull property. I can declare an operator plus that takes 2 ints and returns a db int. And I can declare an implicit conversion from int to database int and an explicit conversion from database int back to int. And this allows me to write code like the code you see in the purple box. Very nice, readable code in a completely extensible fashion. So I talked about earlier, this boring concept called versioning, and now I'm going to bore you with it some more. Versioning it's an interesting problem, actually, and it's one that we thought about a whole lot. And it's and the more you think about it, the more you realize how overlooked it is in other languages and how it actually is a key contributor to a lot of the deployment and maintainability problems that we see in systems today. Both C++ and Java suffer from the fragile base class problem, that the fact that through versioning of components you can break code. And it really boils down to the notion that users are unable in the languages to express the versioning intent. And I think the best way to demonstrate it is really to show you a little example here. Let's say we have a base class. Let's say Microsoft is providing, or you're providing it in some library, and you ship version 1 of this base class. And then the user comes along, a user of yours or our library, and creates a derived class that inherits from the base class. And the user has caught on to the fact that, foo-ness is becoming very interesting in the world, and he wants his object to have a foo method. So he introduces a virtual foo method in his object. And all is dandy. And now, through popular demand, the author of the base class library catches on to the fact that foo-ness is really becoming important in the world, and we better add a foo method to our base class. So in version 2, they add foo to the base class. What happens? It sort of depends on what language you look at here. If you look at C++, well, first of all, C++, as we know it today, doesn't have a binary versioning story. You couldn't just drop a new binary version of the base class and expect the derived class to work. But if you recompile the derived class against this new base class, the compiler will erroneously think that the foo method in the derived class is an override of the foo method in the base class, which clearly is not right, because that base class method wasn't there when the derived class was written. And gosh golly, by pure chance, it might be that you meant the same thing, but chances are you didn't. If you look at what happens in Java, pretty much the same thing. The system assumes that the derived class is an override of the base class, which is wrong. In fact, if the derived class in Java had the return type int, then the system would fall over and flatly refuse to load the derived class now, because it assumes that it's an override. It erroneously assumes it's an override, and it says, the return types don't match. I can't load this class. So this is like one of those, gnarly little problems, that cause systems to fall over. In C#, this code continues to work binarily and from a source code perspective. You can drop version 2 of a base class into a system, and what you end up having, you could drop it in a binary form, and what you end up having now is 2 foo methods. One in the base class, one in the derived class. The derived class hides the foo method in the base class, which is fine, because the derived class was written at a time where the base class didn't have the foo, so there's clearly no dependency on that foo. Now, from a source code perspective, if you recompile derived against version 2 of the base class library in C#, the compiler will report a warning, not an error, but a warning that says, warning, you are hiding an inherited method. Are you sure that's what you mean to do? Now, the code will still compile, so we're not breaking your code, but you can shut up the warning by putting a new directive on the base class. So you can say, yes, this is a new public virtual foo. I mean to hide the base class method. The warning goes away, code continues to run. You could also determine that, gosh, I really like this new foo method that this version 2 of the base class library has produced. I will create a new version of my derived class that requires version 2 of the base. You can express that fact, and then you can say, and now I want to override foo, the foo that I inherited. But the key here is that unless you say the word override, it ain't an override. And that's the only way to make this problem go away. I mean, it's the only way to solve the problem is give the programmer a way to express his intent. And that's what we've done. Now, thank you. Now, I could bore you endlessly with this. I mean, there are many other problems like this, like how do we do overload resolution in constructors and methods and operator overloading in a versionable fashion such that a base class doesn't come along later, add something, and all of a sudden that gets picked by the overload mechanism instead of the other. Interface implementations, I talked about how we give you the ability to implement 2 interfaces that have methods by the same name and give them different implementations. These are real problems, but they're boring problems. But nonetheless, we spend a lot of time on them. C# supports conditional compilation, albeit in a reduced fashion from C++. One of the really tough features to support from C++ is macros, and we don't support macros, simply because they're the death of any kind of incremental compilation or RAD tool or code analysis tool. The fact that you can tickle a macro and the entire source code becomes something else is simply deadly. We do, however, support solutions to some of the things that people often use macros for. Like one classical example, I think, is the assert method, the assert macro that, is a macro that takes a bool and a string, and if the assertion fails, then, it prints out an error message and terminates the app. But, only in the debug version. In the retail version, you simply, have a macro that does nothing, or the implementation of assert is nothing. Now, we give you the same functionality in a type-safe fashion that doesn't require macros. So say you want to write a debug class and you want to have an assert macro or an assert method in there, And it takes a bool and a string such that when you use assert, it's nicely type checked. And if the assertion fails, then this thing, throws an exception. Now, this is great. In the debug version of your program, you can insert calls to debug.assert, and in the debug version, those things will cause your program to blow up if the assertion is false. However, in the retail version, what you could do is you could just substitute an empty implementation of debug.assert, but you'd still be stuck with all the calls to this empty method. What we give you is the ability through an attribute to specify that this is a conditional method. And we do that with conditional attribute. And what it actually means here is it says, when compiling a call to debug.assert, if the conditional symbol debug is not defined, then throw away the entire call. And that's what the compiler does. So basically, in a retail version, you can make this stuff go away, but in a debug version, you still get type-safe argument checking. Okay, the last thing I wanted to talk about is this thing we called unsafe code. Let me try and set the stage a little bit first. The .NET framework and the Common Language Runtime provides you with great interoperability with COM. Any COM class can be directly imported into the .NET framework, and any .NET framework class is automatically a COM object. And pinvoke allows you to just put an attribute on a method declaration that says, hey, this method lives in this DLL, and now you can invoke entry points and DLLs and so forth. So we already have a lot of great support for interoperability. But we still do recognize that sometimes there's a need for you to either call this gnarly API that takes a pointer to a struct containing a pointer to another struct or whatever, something that is just like impossible to express to the interoperability layer. Or sometimes you really want to eke out that extra bit of performance by manipulating pointers, doing unsafe casts, et cetera, et cetera. For that, we give you the ability to write unsafe code. But this code is not something that you can just, write and then download over the internet and open up all sorts of virus problems. It is integrally tied into the security system in the runtime. When you use unsafe code, your code is also marked as being unsafe and unverifiable and subject to stringent security checks. It will not execute if it was downloaded from an untrusted domain, for example. So yes, you can use unsafe code, but that does not mean that we're opening some trapdoor for unsafe stuff to come into the system. However, what it does mean is that you don't fall off a cliff the minute you have to access some sort of functionality that already exists out there that you don't have the capability of changing. You don't want to spend the time rewriting it. You simply stay within the box and you express your intent to the system that, yes, I'm writing unsafe code. Make sure to do the right thing with respect to security, but then give me the ability to do it right here. Unsafe code is sort of like having inline C within C#. You can declare pointers. You can do pointer arithmetic. You can allocate objects on the stack, as you see in this little, or allocate data on the stack, as you see in this little example. And furthermore, we give you the ability to integrate this code with the garbage collector. Now, as you may have heard, the Common Language Runtime supports a mark and compact garbage collector. And what that really means is that there's a thread running in the background that squishes memory and gets rid of dead wood, so to speak, or dead objects as your app is going. And it does it for you automatically. But it also means that objects might, at any given point in time, move around in memory. Now, it doesn't matter as long as you're using safe code, because you never actually see these pointer values and you never manipulate them. But when you're writing unsafe code, if you obtain just the address of some garbage collected object, and then the garbage collector sweeps by and moves the object, then clearly you have a problem. You're now poking into some other piece of memory. To enable this sort of interoperability, we have a statement called fixed that you can only use in unsafe code, but it allows you to pin down an object and obtain a pointer to the object, meanwhile informing the garbage collector that should garbage collection occur, don't move this object. As an example of some of these concepts, let me just show you, this is actually a little snippet of code from the base class libraries that shows you how we are implementing the file encapsulation. So all, input sources in the base class libraries are streams, and so a file is a descendant of the base stream class. And of course, it's an encapsulation of an OS file, which is characterized by a file handle. So we have a handle instance variable here. And to read from a file, ultimately what we end up doing is we call the read file method in kernel 32, the one that you get when you _include windows.h, basically. We use an attribute here to say import this method from the kernel 32 DLL. And here you see the prototype for it. It takes, a handle and a pointer to a buffer, et cetera, et cetera. But in our file encapsulation, we don't want the user to have to deal with pointers because that would require him to have full trust. Of course, this code can be granted full trust, but the user of this code might not have full trust. So we want a method on this file stream that doesn't require the use of pointers. So we have a read method on file stream that takes a byte array and an index and a count, and it basically says read into this byte array at this index and this many bytes. In the implementation, what we do is we use the fix statement to take this buffer, which is a garbage collected object that the user gave us, and pin it down and obtain a pointer to the first byte in the array. And now we can perform, unsafe pointer arithmetic. We can take that pointer to the first element of the array, add the index to it. We can take the address of a local variable because we are in an unsafe context, which we've indicated by putting this unsafe keyword here. Now, as I said, and I'll stress it again, because we put that unsafe keyword here, this class must be fully trusted by the system. And that's fine, because we're writing a file encapsulation here. And of course, at some point, the rubber has to meet the road. But the user of this class is not required to have full trust. So you see how that ties into the security system, and you also see how, we did not have to resort to some sort of external native code mechanism in order to get the job done. We can stay within the box, clearly express our intent, and cooperate with the operating system to make it all work. So that's the end of my talk. Before I take questions, I want to recommend that you go and see Joe's advanced C# talk where he's going to show you some more demos, drill into some more of these concepts. It's in this room right after my talk. Also on the PDC discs or CDs, there's the C# language reference that gives you a complete reference to this language. Of course, the compiler is there. I hope you'll go play with it. I hope you enjoy it. Hope you have as much fun as we did writing it. Thanks for coming.